In this video, we're going to continue talking about our electrophilic aromatic substitution reactions, here focusing on a reaction referred to as sulfonation. As in the last videos, we will be looking at this reaction by going through the mechanism of how we go about replacing one of the hydrogen atoms from benzene with our sulfonyl group. And in the case of a sulfonation reaction, just to point out a few things before we get started into the mechanism. When we are looking at the reactants for this reaction, you will see benzene, or in some of the upcoming videos, a benzene derivative, reacting with a mixture of SO3 and sulfuric acid. And by the way, this is sulfur trioxide is the name of SO3. You may also see this mixture of components labeled as fuming sulfuric acid. And what that is generally a mixture of about 7% of the sulfur trioxide present in sulfuric acid. And you may also see this reaction written out with just the SO3 as well. So just be aware there's a few different ways that you may see this. You may see it as either one or the other of these reactants listed. You may see it as both listed, or you may see it as fuming sulfuric acid. And the purpose of this being the fuming sulfuric acid with both of these is that's going to facilitate the reaction in progressing smoothly. We'll show that as we go through the mechanism for this. And then the product of the reaction, which we have right here, is either going to be an aromatic ring with an SO3 group attached to it, which will have a negative formal charge, or if the environment is acidic and there's protons available, then there will be a proton here and no formal charge on this group. So we'll get into that a little bit more as we go through the mechanism and some specific examples of this. So let's go ahead and take a look at the sulfonation mechanism, where we are going to react fuming sulfuric acid, which is that mixture of SO3 and H2SO4 with our aromatic molecule to ultimately result in the replacement of a hydrogen atom from the ring with an SO3 group or SO3H. So the first step in a general electrophilic aromatic substitution mechanism is usually that we need to make a stronger electrophile. But in the case of the sulfonation mechanism, our sulfur trioxide itself is a really powerful electrophile. So SO3, without even anything happening to it, is a powerful electrophile. And so, technically, it is not even necessary for SO3 to undergo that first step of being transformed into a stronger electrophile. It is a strong electrophile in and of itself. So unlike the other reaction mechanisms that we've looked at so far for things like nitration and the Friedel-Crafts alkylation and acylation and our halogenation reactions, we don't really need to make this a stronger electrophile in order to get it to react. Now, do keep in mind that we have SO3 and H2SO4 present in the reaction mixture. And so what is actually present in the reaction mixture is that rather than SO3 being just SO3, there is an equilibrium going on where our thionyl or sulfur trioxide, is reacting with the acid like so. So I'm going to go ahead and draw out my SO3, sulfur trioxide. Sulfur can exceed the octet rule, and particularly in these inorganic compounds, it often does. And so I'm drawing out my sulfur trioxide, SO3, and I'm also going to draw out my sulfuric acid, specifically just one of those hydroxy groups from the sulfuric acid. So I'm going to show out the hydroxy group explicitly of H2SO4, and then show the rest of it like this. So this is our sulfuric acid, H2SO4, and I'm just explicitly highlighting this portion of the molecule. If you draw out the Lewis structure for sulfuric acid, you would see a hydroxy group in there. And the reason I'm doing that is to illustrate to us that what can happen in this reaction is there will be an equilibrium if you're using fuming sulfuric acid that corresponds to the reversible reaction of our SO3 with our sulfuric acid, H2SO4. And the way that works is that our sulfur trioxide is going to come over and grab a proton from the strong acid, from the sulfuric acid. So let's show that happening. So we're going to take one of the three oxygen atoms here. They're all equivalent that are bonded to the SO3. It's going to come over, grab a proton from the very acidic sulfuric acid. The sulfuric acid is eager to lose that proton. So there's an equilibrium that will go on here between the left and right hand sides of this equation that end up giving us a mixture of this particular substance, SO3H, which I'm just going ahead and drawing in here, like so. And as our conjugate base product, since we deprotonated our sulfuric acid, we will have an oxygen anion there bonded to SO3H. So this is our conjugate base that resulted from deprotonating our sulfuric acid. And so as a result of this equilibrium in the reaction of SO3 with H2SO4, there are actually two different reasonable electrophiles in this reaction, or prevalent electrophiles. One of those is just SO3 from this side of the equation. The other is the protonated form of that over here. So either of these electrophiles can be used in the next step of the mechanism. So both of these will act as our electrophiles. And so let's zoom out a bit and take a look at the next steps of the mechanism. We're in this first step. We were showing that the SO3, when we mix it with sulfuric acid, is not present just as SO3, but it's also present as this other electrophile over here. But since sulfur, SO3, is itself quite electrophilic, we can use either of these two as our electrophile in the upcoming steps. So in this specific example, or this specific reaction, what we've done here at the first step is we've created a mixture of potential electrophiles by reacting SO3 with H2SO4. And now when you look at reaction mechanisms, what you will often see for the sulfonation mechanism at this next step is you will see the reaction mechanism shown with one or the other of these two possibilities. I'm going to show them both to you here just for illustrative purposes, but in the future when you're writing out these mechanisms, you can use either one, pick one or the other. You don't really have to list them both. It's not wrong if you list them both, but you don't have to list them both. And so I'm going to take the aromatic ring here, and I'll plug in those hydrogens just so that I can keep track of who will have a formal charge and making sure everyone's following the octet rule. I'm going to use the SO3, our electrophile that was on the left up here, circled in pink. And of the atoms present in that SO3, the electrophilic atom is definitely the sulfur atom. That is the atom that will be positively polarized. It's quite positively polarized because the three oxygens are electron withdrawing by induction because they're more electronegative than sulfur. They're also electron withdrawing by resonance because we could show the pi electrons moving up onto one of the oxygens. So we'll come over and have the pi bond attack the SO3. And as that happens, what will also take place here, so that sulfur can maintain its neutral formal charge, is that the pi bond will come over onto the oxygen atom. And so let's go ahead and draw out the product of this step. So we've disrupted aromaticity to give the so-called rhenium ion, where we'll have our sulfur directly connected there. Sulfur will have two pi bonds to oxygen, going ahead and sketching those in. It will also have a single covalent bond to oxygen. That oxygen has three sets of lone pair electrons, and hence a negative formal charge on it. We'll also end up with a positive formal charge over here in our rhenium to allow the net formal charge to be maintained from our starting materials here, which had no formal charge overall, to over here, likewise no formal charge overall because the positive and negative cancel out. And then the other possibility And like I said, you can list either of these or both of them as your second step of the mechanism, is that in this second part of the mechanism here, where we are having our pi electrons attack the electrophile, we can have those pi electrons, instead of attacking SO3, it could instead attack our SO3H, which we had formed in the earlier reaction by reacting SO3 with sulfuric acid and stealing a proton from sulfuric acid to give this SO3H. So let's show that mechanism, and it's going to look very analogous to what we just drew up top here. So we have our aromatic ring, hydrogen, hydrogen, draw in my SO3H, positive charge on that oxygen atom, another double bond down here, coming over with my reaction arrow, and I'm going to go ahead and move my electrons over here to attack the electrophilic sulfur atom. That is going to force one of those pi bonds to move. The one that's going to be most favorable to move is going to be this one right here, because by moving this pi bond up onto the oxygen, we can get rid of that positive charge on the oxygen to minimize the total number of formal charges within the product of this reaction. And if we'd instead moved one of the pi bonds over here, we would still have that positive charge up here, and then we would also have introduced a negative charge on one of these other oxygens. And so that's going to be less favorable than the scenario where we just take the pi bond from here, move it up onto the oxygen in order to keep our sulfur here with those grand total of 6 bonds that it likes and prefers. So hydrogen here, and then we'll go ahead and attach our sulfonyl group. So we have our sulfur double bonded to 2 oxygen atoms, 1, 2. We have a single bond here. And that single bond, I need to show how that formed. That formed by taking the pi bond, so we're looking back over on the reactant side. Pi bond came up onto the oxygen like so to give us a single bond here and get rid of that positive charge as we were talking about, but which I had not listed the electron pushing arrows for. So we have an OH right here, lone pair. And thinking about formal charges, we're going to have a formal charge on the rhenium ion right here, and that keeps the net formal charge constant and going from the starting material mixture to the products, because in our starting material we had a net charge of +1 because we just did the positive charge here on the oxygen, and now in our product we have a net charge of +1 as well. And so then at this point what's going to happen in step 3 is that we take either one of these 2 possible intermediates, and we are going to go through step 3 of losing the proton to restore aromaticity. So this is going to be our beta elimination step. So let's take a look at that. I'm going to go ahead and zoom out here so that we can do so. So going ahead here with part 3, our step where we're going to lose the proton to restore aromaticity using mechanistic electron pushing arrows, very, very analogous to what we've done in earlier videos with other types of EAS reactions. So I'm just redrawing the product of the previous step there. And I'm going to abbreviate for now my SO3. I'm going to put that negative charge on there because we had a negative charge right here. So the charge on this is a net negative charge. So that's why I put SO3 minus. I'm putting my positive charge over here on that carbon that only has 3 bonds to it. And what's going to happen here is that we'll bring in a base to grab a proton from the beta position, beta relative to this alpha position that has the carbocation. So we come over to here to the beta position, grab a proton here, that's going to force the bond between carbon and hydrogen to come over to restore the aromaticity. So let's show that happening. And what will we use as our base here? So as we look back at what we have available as our base, there are always a few different possibilities. One of those is that we generate this conjugate base of SO4H minus up here, so we could use that as a possible base. Also, if there were any water in the reaction mixture, we could use that as well. So we're going to bring in our base in order to do that. So I'm listing explicitly that oxygen anion atom from the SO4H. So I just took this and copied it down from up here. And what we'll do is, that's acting as our base, bring the electrons over to grab our proton from our rhenium acid. The rhenium is very acidic because this is an unstable reactant relative to the product that will be aromatic and hence very, very stable. So the reaction is very favorable in going toward the side of the product. So you just need a very weak base here in order to grab that proton, because that proton is very, very, very eager to be lost, since the product of losing that proton will be a very stable aromatic compound. So going back to your acid-base concepts, we would consider the pKa of an rhenium to be super duper low because of the fact that the product side of the equation, where we've restored aromaticity, is much more stable than the reactant side of the equation. And so what happens here is our base came in, grabbed that proton, the electrons came down to restore the aromaticity that I'm highlighting over here in that new pi bond that we formed. And we would still have our SO3 anion right here. And to fill this completely out, we would also have regenerated our H2SO4 sulfuric acid. We can do the same sort of game for the other rhenium possibility that we drew, the one right here. Remember that you can use either of these two. You don't have to draw them both. You could draw them both, but they're both possible scenarios for how the reaction can progress. And so I'll redraw that. So redrawing my other possible rhenium intermediate, SO3H in this case. So we plug in our OH, like so. And now we will go ahead and react with a base. And reacting with a base here, one possibility is that we'll bring in the same base we used up there, which was our deprotonated sulfuric acid. SO3H there, plugged it in, bringing the lone pair electrons over, acting as our base to grab a proton from the acid there, grab a proton right there at that beta position, and I should have put a positive formal charge in there on the rhenium, so I put that in right there. And the bond is going to come over to be transformed into a pi bond here, and we'll go ahead and draw out the final product of that set of electron pushing arrows, where rather than having a negative formal charge on that SO3 group, instead it has picked up a proton earlier in the mechanism, so it's an SO3H group, and therefore there is no formal charge on that group. So SO3H will be what we'll end up with there, plus H2SO4. And in actuality, these two products, where we have SO3 minus or SO3H, can be readily transformed between one another based on what the exact conditions are in the reaction mixture, or based on what pH you bring the reaction mixture to at the end. So in the case of the bottom scenario, this proton that I'm highlighting in the product is relatively acidic, meaning it's relatively easily lost. So if the reaction is under conditions that are neutral or basic, this is going to be lost and you'll have SO3H. On the other hand, if you're under very acidic conditions, the proton will be favorable to stay there because you're in an environment that is rich in protons, and so it will remain attached. So the actual structure of the final product is going to be dependent upon what conditions the reaction is in. And you may be saying to yourself, well, I look at the reaction mixture and it looks acidic, H2SO4, but at the end of these reactions, very commonly what people do as they're purifying the product is they alter the pH. They bring the pH into a neutral range, and so that could result in the loss of a proton here. So if you're asked to provide the product of this type of reaction, generally you can list either of these two products, because whether that proton is present or not is dependent upon the exact environmental conditions that this system is found under. Because if you're in a strongly acidic environment, you're going to have this product, If instead the conditions at the end are altered so that it's not a strongly acidic environment, you will have this one. So either or I would take here. And likewise, going through this full mechanism, either of these two routes are ways to go about getting to the sulfonation product. So keep that in mind as we are going through these.